All right, guys, let's go ahead and get started with these inclined plane notes. And when we say an inclined plane, we're just talking about a tilted surface, sometimes called a ramp or an incline. So as you can see below, this would be an inclined plane. So let's say that we have some object on this inclined plane, and let's just go with a box because we're really familiar with boxes. So here's our box on the inclined plane. The first thing we're going to need to do is draw our free body diagram like we always do. So if I draw my free body diagram for this box on this plane, you'll see that I have force gravity pointed straight down because force gravity always pulls straight down. Then I notice that this inclined plane is a surface, so it's exerting a normal force from that surface. Normal force is exerted perpendicular from the surface. So the normal force should be pointed up at an angle in this case. And here's my normal force. So we can see that normal force is at an angle to this incline. And if I were to bring this normal force over here, you can see that it's just perpendicular to that incline. The other thing that has to be present here is friction, and friction is going to point parallel to this incline. So I got force friction pointing up the incline. Why is it pointing up? Well, it's pointing up because if this box were to move, the box would move down the incline like so. Also, you're going to notice that force normal and force friction are perpendicular to each other as well. And that's going to be the case always when we are on an incline. So something funky that you're going to notice too right now is that we're normally used to writing our coordinate system like this, where we have up as the positive direction and to the right as the positive x direction. But if we do that here, we're going to notice that we have two forces that are both in the x and the y, because force normal points up over here and force friction points up this way. So it's a combination of both. That's going to make things a little difficult. So we're going to go ahead and turn our coordinate system. So when we turn this coordinate system, we're actually going to make it so that our coordinate system is parallel and perpendicular to the incline. So here's my new coordinate system here. I notice that my x direction is now parallel to the incline, and my y direction is now perpendicular to that incline. By doing that, it's going to make force normal a line in the y direction and force friction a line in the x direction. The only force that is going to be a combination of both the x and y now is going to be force gravity. Something important to note about this coordinate system is that if there is acceleration, it's only going to be along the parallel axes of the incline. And in other words, that's just saying that we are only going to accelerate in the x direction when we have an inclined plane. So let's go ahead and write our net force equations. So net force in the y direction is going to be equal to the forces that point up in the y direction. Given that this is our new axes, we notice that force normal is pointed up in that direction. So I'm going to say force normal minus, and then I'm going to notice that force gravity is in the x and the y direction. Because if this is our x direction here, and I see force gravity is pointed in this direction, it's going to mean that force gravity is a combination of both the x and the y. So if we remember, forces are actually vectors. And since they're vectors, we can split them up into different components. Since we notice that force gravity is in the x and the y direction here, we're going to go ahead and split it up so it's only in the y direction. So I'm going to go and bring force gravity down here, okay, so we can really see this. So here's force gravity. And then I'm going to draw my axes like I had up here. I'm going to make them kind of small though, so I have plenty of room to write force gravity. So I see here's my y and here's my x. So if I were to split this up now, I'm going to notice that force gravity in the y is just going to be parallel to the y direction here. So this would be force gravity in the y direction, or the y component of force gravity. And then force gravity in the x is going to be parallel to the x direction here. So this one down here would be force gravity in the x direction. Now that we split it up, we can go back and fill out our net force equation. So force normal minus force gravity in the y direction. And that's going to equal mass times acceleration. Fortunately, we know that the box is not accelerating in the y direction, so the net force here is just 0, which means that 0 is going to equal force normal minus force gravity y, which is telling us that force normal in this case is going to be equal to force gravity in the y direction. Let's go ahead and do the same thing for the x direction now. And in the x direction, we have net force in the x is equal to the forces that point to the right. Well, this is where things get tricky. And the force that's actually pointing to the right in this case, we're going to notice, is force gravity x. So we're going to say force gravity x minus the forces that point to the left, force friction. And we know that those are equal to mass times acceleration in the x direction. We are experiencing some acceleration in the x direction, so there's nothing else we can do here to simplify this part. So now that we have a force gravity x and force gravity y, we need to figure out what these actually are. And the way to figure that out is by taking the angle of the incline right here and realizing that this angle that the incline is forming is the same angle that is happening right here in our force gravity vectors. There's a very long mathematical proof to show this, but for the sake of the video, let's just all agree that this is the case. So if I do that, now I'm going to notice something. Well, I remember that force gravity is just equal to mass times gravity. So I see this is forming a 90-degree angle. So this part of the triangle is my hypotenuse. So the hypotenuse is mass times gravity. The angle is just the angle theta. I don't know what it is at the moment. Obviously, in my problems, though, it will most likely be given to me. So this will be some given information. So with that being said, we can find out now that force gravity in the y direction is just equal to mass times gravity, because this is really what force gravity is. It's just mass times gravity times, and this is the adjacent side here. So since it's the adjacent side, we're going to use cosine of theta. And we find out that force gravity y is just equal to mass gravity times cosine theta. Let's do the same thing for the x direction. We get force gravity in the x is equal to, well, we notice that the x side is the opposite side. So that's going to be sine. So that's mass times gravity times sine of theta. These equations will always hold true for when we're on an incline and solving for force gravity x or force gravity y. These are not equations that I will give you, though, unfortunately. It is something that you will have to know. And the way that you would know is just by setting up a simple math problem like we did here. We drew our angle, we drew our triangle, and then once we had the triangle, it was pretty easy to see what was happening here. This is the opposite side, this is the adjacent, and this is the hypotenuse. So once we had all that information and we had our theta, we were able to figure it out from there. Something really important for you guys to note, and a place where a lot of people make mistakes, is that a lot of people mess up this part here. They think force gravity y is sine, and they think force gravity x is cosine. The reason being is that people are really used to drawing their triangles like this, with their angle right here, and seeing that, well, this is the y direction. So the y direction is the opposite side, so it should be sine. That would be the case if we were talking about forces applied at an angle, which is going to be our next topic. But for forces at an incline, because of the way that this angle identity works, the adjacent side is actually the y part of our triangle. So really, really important. So please, please, please write this down somewhere, memorize it. All right, but this is what we need to know, is that force gravity in the y is mass times gravity times cosine theta. And force gravity in the x is mass times gravity times sine theta. So let's take a quick second and see if we can really understand what these equations are telling us. So again, we had net force in the y direction was equal to force normal minus force gravity y. And force gravity y is mass times gravity times cosine theta. We had net force in the x direction, which was equal to force gravity x, which was mass times gravity times sine of theta, minus force friction. But something important to note here is that force gravity in the y direction depends on cosine theta, and force gravity in the x direction depends on sine theta. Let's look at cosine and sine theta and see if we can notice a few things about it. Well, the first thing to note is that cosine of theta is going to have some set value from 0 to 90 degrees. And we're going to note that cosine of 0 is actually going to equal 1. So that's where the maximum value occurs. And cosine of 90 is going to equal 0. That's where the minimum value occurs. So sine of theta is going to have set values just like cosine of theta, and that's going to be 0 to 90 degrees as well. And we're going to notice that sine of 0 is going to be 0, because that's where the minimum value occurs. And sine of 90 is going to be 1, because that's where the maximum value occurs. So some of you might be asking yourselves, well, why are you bringing this up? Why is this important? Why does it matter? Well, it matters for a few things, and it's going to help us conceptually understand what's really happening with these inclines. Because this theta in these problems, so cosine theta and sine theta, is the angle of our incline. So we can see here that as this incline increases, or the angle gets steeper and steeper, our force gravity in the y direction is getting smaller and smaller. What does that mean? Well, that means that our force normal is getting smaller and smaller, because we know that these two things are balanced to each other because we're not accelerating in that y direction. But as the angle of the incline increases in the x direction, the force gravity of x is getting bigger and bigger. Why does that matter? Well, if this is getting bigger and bigger, we know that this is equal to mass times acceleration. So that means that our object is moving faster and faster down that incline. So this is really just common sense. We've seen this before, right? If we were to go sledding and we were to go down a hill that looked like this, we would call this kind of a bunny hill. It's kind of weak, right? Some weak sauce happening right here. We're not really going too fast down that incline. The reason being is that the angle is very small. But say we go down a hill that looks like this. This is like a triple black diamond here. All right. This is some high quality stuff. A1 right now. How fast are we going to be going down this incline? A whole lot faster than we would down this incline. So summarizing what we just talked about, as the angle of the incline increases, force gravity in the y direction decreases. And since force gravity in the y is equal to force normal is also going to decrease. But force gravity in the x is going to increase, and because force gravity in the x is increasing, our acceleration in the x will also increase. On the flip side, the angle of the incline decreasing, meaning that it's approaching 0, meaning that our incline is basically becoming a flat surface, force gravity in the y is going to increase. And again, since force gravity in the y is equal to force normal is also going to increase. Force gravity in the x, though, will decrease, and acceleration in the x will decrease. Think about an object laying on a flat surface. It doesn't just randomly accelerate to the right because of gravity. Last thing I want to talk about is just some common mistakes, and that's that force normal does not equal force gravity. Okay? So that actually was never really the case. We just simplified it and said that that was the case on a flat surface. But if you notice really quickly, on a flat surface, right, the angle is just 0, meaning that force normal is still and has always been equal to force gravity in the y direction, because force gravity in the y is mass times gravity of cosine of 0. Cosine of 0 is just 1. So force normal is just equal to mass times gravity, which is kind of funny because we've actually been using this equation the entire time. It's just that since we've been on a flat surface, this angle has always been 0. So it's always just been simplified to mass times gravity. So please, please, please remember that force normal is not just equal to mass times gravity. It's equal to mass times gravity times cosine of theta.